Welcome back. I've been doing scenery a lot lately, so as a change of scenery from scenery, I'm going to talk about craft beer. Japan has a really good craft beer scene, and most people don't see it simply because the big brewers like Asahi just so massively dominate the market. But if you go looking for it, you can actually find it there. And the background here is one of my favorite, what they call tachinomi, sort of a stand and drink place. And so if you have a look, you can see it's actually kind of tiny. Maybe holds about 16 people on a busy day. Serves up craft beer from all over Japan. There's actually quite a lot of craft beer being made in Japan now. And all over the world as well, and you can get food and so forth. It's a really good place to go. If you're interested in finding it, it's in a suburb called Naka Meguro in Tokyo on the west side. And it's one of those nice suburbs that people tend to go to because of another part that's sort of, funky shoppy district or something like that. But a lot of the little suburbs in the west of Tokyo are gentrifying quite rapidly and have lots of nice little businesses like this popping up, and I figured I'd give these guys a plug. So if you're ever in that neck of the woods, Beer Boy is a good place to stop by. Alright, so we were just dealing with Euler-Lagrange equation, and we just pulled it out more or less via simple calculus on asking questions about lengths of paths, okay? And so what I want to do now is loop back around quickly onto the lazy walker problem to use the apparatus we just built to basically demonstrate that the shortest path between 2 points must be a straight line. So let's bring that problem back down again. So where we got to with it was we had an expression that looked like this. Integral between 1 and 2 of square root of 1 plus y dash of x squared dx. And what we want to do is minimize that, okay? So I like in physics problems to actually break them up into sets of steps because often there's processes that you apply again and again and again, and it's useful to do the steps so that you don't forget anything. So step 1 here is going to be, we're going to get f, y, y dash, and x, right? Because to bolt it into the problem that we just did to get our Euler-Lagrange equations, we're going to want to know what that thing is. And so we can see that already. It's up on the line above us. Let's write it here in a slightly different form though, as 1 plus y dash squared to the half, okay? And just to be really clear, that is y dash squared and not y to the power of 12, okay? All the way through this lecture, there won't be any powers of 12. They'll all be squares of probably something with a dash. Okay, so that's step 1. We're clear on that. The second step here is to deal with our Euler-Lagrange equations. And the first step of this is going to be getting these two derivatives with respect to y and y dash that you can see up in the lines above, okay? So let's do this. df on dy for this function just here is going to be 0 because there's no terms in y. And then df on dy dash is going to be, is definitely going to have a term because we've got a y dash in that line above. And so the way we do this is we bring the factor of half from the exponent, we bring the derivative of that function, so it's going to be 2y dash, and then multiply that by the function that we had, 1 plus y dash squared, now goes from a half to a half minus 1 is minus a half, right? Like so. And then we can rewrite this thing. The half cancels the 2, so this is going to be y dash, and now it's going to be on top of 1 plus y dash squared here. Okay, so that's what that looks like. All right, so now we can just pull together our Euler-Lagrange equations. So it's going to be df on dy minus d on dx, df on dy dash. And so it's going to be equal to the first term up there is 0. Okay, so that's that one. And then minus d on dx of y dash on square root 1 plus y dash squared. Okay, and of course that's going to be equal to 0 because that's also built into our Euler-Lagrange equation. Okay, all right, so we've now got it. Step 3 in here is to basically solve what pops out. And there's a couple of things that happens when you deal with Euler-Lagrange equation, right? One is a nice situation like we have at the moment where one of the terms here is 0, and so it vanishes, and what you've really got is d on dx of something equals 0, right? Because you can automatically integrate that back up to a solution. You also get the case where this term out the front here is not 0, and in that case you have to do a little bit more work on it, okay? So this one ends up being kind of nice. We can integrate both sides, and so what we'll get here is y dash on 1 plus y dash squared is equal to a constant. And then that gives us, we can basically multiply the denominator up. So this is now c 1 plus y dash squared, where c is just a constant, okay? We can square both sides to get rid of this square root just here. So this is now y dash squared is c squared 1 plus y dash squared. And let me just make that c obvious up there, just so that no one thinks we're talking about speed of light or something crazy like that. Oh, and the square root's gone. So that's just that. And then, of course, we can multiply this out now. So this is going to be c squared plus c squared y dash squared. What we can do is collect the terms in y dash all over to one side, right? So this is now going to be y dash squared minus c squared y dash squared equals c squared. And then we can collect the y dash term on the left hand side. So this is now 1 minus c squared y dash squared equals c squared. You can probably see where I'm going. I'm going to pull my y dash squared out here and just put a bucket of constants on the right. C squared on 1 minus c squared. And then this c squared on 1 minus c squared is just a constant, right? It's just a lump of constants. So this thing is a new constant. We'll call it d. We don't really care what it is, right? And this is one of the skills of doing problems in physics. You start to get the hang of when you care about constants and when you don't really care about constants. Okay, actually, let's be kind of cheeky and we'll just call it a constant d squared, right? If d is a constant, then d squared is also a constant. And so we can take the square root of both sides here, and basically what we've got is y dash is equal to d, right? So the solution to this problem is essentially that y dash is a constant. Let's think about this for a second. Y dash is dy on dx. So what this has said is that dy on dx is a constant, and you can kind of see that it's already screaming at you that this is a straight line, right? But let's write this explicitly, dy on dx equals constant. We can take this one step further if we really want to, right? And I often have this as a step in these problems, which is to find the meaning, because in the end that's our job in physics, is to get mathematical solutions and then attach a meaning to them. What we could do here is be a little cheeky. We called it d just because we needed a name for a constant, but actually, since we can see where this is going, what we can do is call this constant m. Hasn't got a meaning at the moment, but that's all right. We know what it is. It's a gradient. And we know it's a gradient because of that line up there, okay? All right, so we can integrate both sides, and if we integrate both sides, what we get here now is y is equal to m. We're integrating with respect to x, so this will get us to x. And then we can have to add a constant of integration here, so we'll add that, and we'll call it b, just to be cheeky. And this time we care about this constant, and we know why we care about this constant, because it's the intercept in a straight line, right? And so you can see here the solution is, if you minimize the length of the path in this particular problem, it tells you that the minimum length comes for an equation y as a function of x, which is the path, that is a straight line, right? The derivative is constant. We'll have to add some constant on to set it to the right position, and it should snap to place between 0.1 and 0.2 in here, okay? This is kind of a nice thing when I did second year mechanics. If I think back to second year mechanics, there was a couple of standout moments in the whole course. And one of them was where you come to this point in this lecture, and for the first time you kind of mathematically prove that the shortest path between 2 points is a straight line. It's something you know is obvious, but you just sit down and actually prove it. And also the problem that I want to do next, which is Fermat's principle. And so this is one place where the shortest path is not always a straight line. And so you can imagine, for example, that you're a beam of light wanting to go from point 1 to point 2 here, which is the two ends of your diagram. And if there was nothing in the way, the shortest path between those 2 points would be to just go as a straight line between the two, okay? Now, the interesting thing that happens here, if you want to get from path 1 to path 2, and we know that it's going to follow this sort of zigzag path in here simply because the way physics works is it chooses the path with the least time or least action or whatever, is actually to come in here and not take a straight line path. You come to this point on the block, you refract into the block, and then you refract out of the block. And so you're not actually taking a straight line path, and that's the minimum time path between those two particular points, okay? And so this is the idea behind Fermat's principle, that light travels a path that takes stationary time. And when we mean stationary, what we're doing is we're taking a derivative and setting it to 0. Now, in most cases, it's the minimum, and so you'll often see this written as light takes the path that takes the minimum time. But there are problems, and there are problems in Lagrangian mechanics as well, where the stationary is not necessarily a true minimum in this problem. So we sort of keep that open. It's a sort of exotic set of solutions. It's not very common, but it can in principle happen. Okay, so let's play with this problem. I'm going to do it in the same form that I saw it in second year. We're not really going to go hardcore into the sort of calculus of variations. You don't need it to do this problem. There's a nice little video on YouTube where someone does it that way, and you have to incorporate heaviside functions and stuff like that to get the mathematics to work properly. You kind of have to add it's one of these really simple problems where you have to add a whole pile of baggage on to get it to work by an advanced technique. For my class, I'll put the link up for that. But here I just want to do it the simple way. So let's take the refraction problem and just distill it down a little bit to something that looks a little bit like this. We've got a y-axis and an x-axis like this. Call this x, call this one y. We've got some point up here, a, and we've got some point down here, b, okay? And what you want to do is get from point A to point B, and the crucial thing that happens in here is the velocity here is different to the velocity here, and the velocity changes as you go from y positive to y negative, okay? And I could draw this a little better. Hang on a second. Let me just move my B. I'm going to pull my B in nice and close here, just so the graph looks kind of decent. And so what we have is we're going to come to this point here, and we're going to call it O, and then we're going to come out of this point here, right, down to B. And so there's an angle in here, theta 2, and there's an angle in here, theta 1, just to spell out our problem. And we need to put some length scales onto this thing as well, okay? So what we're going to do is decide that in going from A to B, if we consider along the x direction, we've got a length L, which is the overall difference between A and B in this direction. So that's L just up there. And then we've got this length just here, which is between our position A and our origin on the graph, so we'll call that x. And then, of course, this little distance in here is going to be L minus x, all right? Okay, now some would have gone, why have I not chosen just the straight line between A and B? Some of it's that I know it's not. Some of it is that what I need to do is set up a variational problem, right? And so what I've done here is allowed my path to vary between the two endpoints. O can move in this problem. It'll look in that graph like it can't, but it can, right, in principle, because I can slide that y-axis along. And when I slide that y-axis along, what I'm doing is I'm changing x, I'm changing L minus x, I'm changing theta 1 and theta 2, but the thing that I'm not changing is big L, right? This big L up the top is set entirely by the positions A and B. And so what I'm really doing is choosing this point here where we intercept the change in velocity between the two media that we're going in, for example, and allowing that to be a variational point that can move, knowing that in a medium with constant velocity, I'm going to go in a straight line, okay? So we're sort of back in the problem we did in lecture 3 in some ways of just varying one point in a path because we know that's the only point that's going to matter, okay? One way to think about this problem is just refraction of light. Travels in different velocities in different mediums. The other way to think about this, I think about it as the triathletes problem. If you're in a triathlon race, you might be swimming from some point back to a running interchange, and the question becomes, do you swim a straight line to that interchange, or do you take some angle in the water and then change angles on the sand, knowing that you're accounting for your two velocities in the two places, okay? So there's lots of places where this sort of problem turns up. Okay, so now we need to turn this into maths. We're looking for the least time to do this. And this is some of the reason why I call this sometimes the triathletes problem, because when you're in a race, you're obviously trying to get from some place to some other place in the least amount of time. So we're interested in the time that it takes to get from point A to point B. And it's going to be the sum of the time to go from point A to point O plus the time to go from point O to point B, okay? Two separate times. And then, of course, we can pull out the distances and the velocities here to get those two times, right? So TA0 or TAO up the top here is going to be this path along here. And so it's going to have a length that's equal to square root of x squared plus y1. So let's just add something on this graph for a second. That's y1 just up there. And then this here is just y2, okay? So this is going to be, oops, black, please, come on, squared. And of course, we're looking at a time, so it's going to be distance divided by velocity, so it's going to be on v1. And then for our second path just down here, we can do exactly the same thing. This is now going to be plus the square root of L minus x squared plus y2 squared on v2, okay? All right, we need to find the minimum time, and the minimum time dt AB on dx, because x is the thing that we can change here, right? We can't really change where that boundary in the velocity change is, but we can change where we head to make that crossing. So we're looking at dt on dx, and we want to make that equal to 0 here, okay? So let's write dt AB on dx. It's going to be d on dx of this first term, x squared plus y1 squared on v1, plus d on dx of this second term, right? Square root L minus x squared plus y2 squared v2. And you'll see here that the sign on v2 on y2 doesn't matter because we're taking the square anyway, right? That's why we didn't care about it very much. Okay, so we know how to take the derivative for this thing. It's basically function rule, same as we would get. So we've got our constant 1 over v1. Then the derivative here is going to be, we've got a square root up the top, so it's going to be a half. Our derivative of the thing inside the square root is going to be 2x. And then we're going to end up with 1 on square root x squared plus y1 squared. Okay, so we basically take the term in the top, which would have been to the power of half, subtract 1 from that, that gets us minus half on the bottom. Okay, so that's the first part. And then the second part in here, and I might have to go over a little bit, is going to be 1 on v2 times a half times 2, and of course when we work this thing out we're going to get minus L minus x on square root of L minus x squared plus y2 squared. Okay, let's pull this just in here. Okay, we can clean this thing up, so this is now 1 on v1 x on square root x squared plus y1 squared, and then there's a minus sign just up here that we need to account for, so this is now minus 1 on v2, and this term over here is now L minus x on square root of L minus x squared plus y2 squared. Okay, all right. And this has to be equal to 0. Now, the interesting thing is, and I'm not going to write this out fully explicitly, if you consider this term just here, what it is this x divided by the length of this, right? And if you think about what that is, it's basically the sine of theta 1, this angle just in here, okay? So this thing becomes sine theta 1. And then the same argument holds for the second term down here. You're basically taking L minus x along this bit here. You've got a Pythagoras term just in here, and so it's going to be the sine of the angle just inside there. So it ends up being sine of theta 2, quite simply. And so what we have here is sine theta 1 on v1 minus sine theta 2 on v2 is equal to 0. And of course, we can carry one term onto the other side here, so sine theta 1 on v1 is equal to sine theta 2 on v2, okay? And so that's the ideal case that minimizes the time that the path takes, and what it says is that what angles you should take in here, okay? Now, the interesting thing to consider here is, imagine we're dealing with light, okay? If we're dealing with light, then V1 is going to be C on N1, and V2 is going to be C on N2, where here C is our speed of light. It's not just a constant, right? And these are your refractive indices. We can substitute that in here. So what we would have is now N1 sine theta 1 on C is equal to N2 sine theta 2 on C. And then, of course, those two C's cancel out, so we're left with, N, not M. N1 sine theta 1 is equal to N2 sine theta 2. And this thing here is just Snell's law. And so you can see here basically this idea of Fermat's principle that light travels the path taken with the minimum time basically just pops out when you consider a problem where you've got a transition between a velocity in one medium and a velocity in another medium into Snell's law. Okay. The interesting thing here is that everyone comes through first year physics and thinks that Snell's law only holds for light. But the interesting thing that we just realized here is that Snell's law holds for anything that is trying to minimize the time that it takes to travel from point A to point B across a change in medium that incurs a change in velocity. And just to highlight this, students in my course, I'll put the actual full paper up on the website for you. It's not just light, but ants also obey Fermat's principle. Okay, so you can see here we've got a material that is kind of rough to walk on. Got a material up here that is very smooth and easy to walk on. And so you take a set of ants, you make them want to go from point A, which is, say, where they live, to point B, which is where the food is. And they, of course, have to get that food back to the nest, and they're going to have a very good interest in minimizing the amount of time that takes, because time spent walking corresponds to loss of energy and how long it takes to get things back to where you're going. And you can see in here quite nicely they actually follow basically Fermat's principle, and they work out a path. And the interesting thing about ants is that they actually leave chemical signatures as they follow paths. And so you really can imagine this to be a little bit like what we've been doing so far in calculus of variations, where you will explore a whole pile of correct or incorrect paths, and then basically correct that back to the ideal path to take, and then everyone starts following that ideal path to take. Okay, so Fermat's principle doesn't just hold for light, it holds for all sorts of problems in here. Okay, all right, so there's one last thing that I want to do for today's lecture. It wouldn't be a good mechanics course unless I did roller coasters somewhere in this, and so I'm going to kick this off by introducing quickly one of my favorite things about working at the University of Tokyo, which is that it essentially has its own theme park, depending on how you define the boundary of the campus. So you've got like a very traditional campus boundary. There's a distinct sort of fence around the campus, but a lot of the nearby streets are essentially, you know, much like on any university. There's buildings that sit outside that because they've had to build outside the perimeter. There's eateries and all these sorts of things. Maybe 5 or 10 minutes walk away from the campus is actually the Tokyo Dome, which the first few times I went to Tokyo, I never realized that this was so close. It wasn't until I lived there that I went, hang on, that's just down the road. And the Tokyo Dome has a little theme park right next to it, and so what you can do during your lunch break if you're working at University of Tokyo is just go down, pick up some lunch, walk a little bit further, have a ride on the roller coaster, and then head back to campus. And so we would do this sometimes. So I'm just going to give you a quick look at the what I guess I'd call the campus roller coaster for University of Tokyo. It's a ride they call the Thunder Dolphin. I don't know where the name comes from. The initial drop is really cool. But the one nice feature is it's actually entangled into a building. And so what you'll notice as we come up over the top of this corner here is you go through a hole in the building wall. And then it sort of loops back around. Has this sort of weird section on the back. And done. And for a sort of middle of the day change of scenery, small adrenaline kick if that's your thing, you can sort of pop out, have a ride, come back to campus and get back into work. It's a good alternate to caffeine to keeping you awake and ready to roll for the afternoon. But it also highlights a really interesting problem, which is sometimes you care about wanting to get from one point to another via the fastest path in a case where you're not really dealing with a straight line. And so this is a problem for roller coaster designers in the sense that you want to get from the peak, which is where you get all your energy from, to your first drop as fast as possible. But the straight line isn't the logical thing to do because you're now subjected to force of gravity and you get your velocity out of that drop, right? When you're sitting at the top, you're actually stationary, and you'll notice from that slide video that I just showed, that actually you come over the top pretty slowly and you pick up speed as you come down. And so what you want to do is have some balance between trying to maximize your drop and getting distance along so that you can make that first fall seem short in time so that it seems like a faster ride, okay? And so this is actually a classic problem that's called the Brachistochrone problem. I prefer to call it the roller coaster problem. And so what we'll do is go through and solve this, because it's a really nice example of using Euler-Lagrange equation, basically just to minimize a path, but to minimize a path that's actually non-trivial sort of path in here. So let's draw ourselves a little graph here to set up the problem. We've got point 1, and then we'll attach a pair of axes to this thing, okay? So this is y, this is x, this is point 1, and this is point 2 down here, right? And then the textbooks that make this not very interesting, it's just like, what's the shortest path between 1 and 2? But let's make this kind of interesting. You've got your initial rise up into your roller coaster, and this is the bit where you just start to get going when you kick over the top, right? And I highly recommend the front cars on that roller coaster. The back's nowhere near as fun. The front is just absolutely scary going into that first drop. And then you're going to want to find your way down here into where point 2 is. And then as a roller coaster designer, point 2 is that transition where you know you're at your highest velocity, and then you want to set up something after it, right? And in this particular case, it's to come up and kick around the top corner onto the top of the building. So we want to work out this path, and we want to work out how to do it in such a way that we minimize the amount of time it takes to get from point 1 to point 2 so that it seems like a really fast ride, okay? And so the question is, what shape should we have for that track? We know that the time to get from 1 to 2 is going to be the integral from 1 to 2 of ds on v, right? We've done this already so far, working through this lecture. And we have one important thing in here, which is that we know that the velocity at any point in time is going to be 2gy, and that's going to come just from conservation of energy, right? Because what we're doing in a roller coaster is we basically take ourselves up to the top, we accumulate some amount of gravitational potential energy that corresponds to a height above whatever position we're interested in, and then as we roll off down this hill, we basically convert that energy into this energy, okay? I'll let you work out for yourself why that v is square root 2gy. It's a fairly simple first year problem, just to keep the time contained. Okay, so v here is a function of y. We know that for sure, right? And so what we're interested in is writing the path not in y as a function of x, but in x as a function of y, right? We're interested in trying to get where we are along this direction as a function of what happens to us in height. So what we're going to do here is actually flip this problem on its head and deal with x as a function of y, because y is the determining variable for our velocity and our energy in here. We need ds. So ds is going to be square root of dx squared plus dy squared. And we pulled this stunt earlier. We can basically clean this up to pull out our dy. So we would have dx squared on dy squared plus 1 dy. And then, of course, this term here is just x of y dash squared plus 1 dy. Okay, so what I've really done here is taken the problem I did at the beginning of the lazy walker problem and now decided I'm actually interested in how y changes as how x changes as a function of y rather than how y changes as a function of x, because I've got to account for a velocity that depends on y. Okay, so now our t12 is going to be integral from 1 to 2 of ds, so that's going to sit on top, x dash of y squared plus 1 dy, divided by our velocity. And our velocity in here is going to give me a term on the bottom, 2gy. Okay? All right. We can pull the 1 on root 2 out the front, just to keep things simple. We can integrate from, let's call the point where we start t equals 0 at the top, and then we're going to be at y2 further down, okay? And so really what I'm thinking about here is just setting my origin for my coordinate system here at this point 1. So this is basically y equals 0, x equals 0, and this will be a point x2, y2. Okay, just pulling a variable out of the problem that I don't really want to have to deal with. So that's y2. And sensible choice of coordinate systems is actually a really useful thing in a lot of problems. Okay, and so now this thing is going to be x dash of y squared plus 1 on root y dy. Okay, so I'm going to do this problem the same way I've done the other ones. I'm going to step it through step by step. So step 1 here is get f. And so we know here that f, and it's a function of x, x dash, and y in this particular case, okay, is just x dash squared plus 1 on square root of y, okay? Okay, so then once we got that, step 2 is our Euler-Lagrange equation. And so here it's going to look like df on dx minus d, it's a full derivative here, d on dy, df on dx dash equals 0. Okay, so we've essentially just done a variable swap. If we consider the f, our df on dx is going to be 0 because there's no terms in x. Our df on dx dash is just going to be x dash on root y square root of x dash y squared plus 1. I've already done essentially that derivative earlier in the lecture, right? So I'm not going to do it again and labour the point. I'll let you do it for yourself if you don't believe me, which is always a good thing to do. Both check if you don't believe me and don't believe me. And so if we now set this thing up to solve, we've got 0 minus d on dy of x dash on square root of y x dash y squared plus 1 equals 0. And we can take the same tactic that we did earlier, right? So we know that term out the front is 0. We can basically immediately integrate both sides, okay? So if we do that, integrate both sides, we've got x dash on root y root x dash of y squared plus 1 equals a constant. And then we can do same trick we did last time, is square both sides to get rid of the square root, right? So square both. Now what we've got is x dash squared on y times 1 plus x dash squared, okay, just to keep the notation clean. And this thing is still a constant, and I'm actually going to be a little cheeky here. What I'm going to do is call this a constant 1 over 2a, right? And the reason I'm doing this is for convenience later on, right? Now, the first time you would do this problem, you wouldn't know this. You would probably just call it a constant and keep working through the problem. And then when you get to the end, you realize actually it would be more convenient if way back there I'd called this constant such and did this. In an exam, you probably don't have enough time to do it. In an assignment, perfectly fair tactic, okay? Certainly not a problem at all. Okay. So what we can do now is we can solve for x dash. And so we can cross multiply this thing out. So this is 2a x dash squared is equal to y 1 plus x dash squared. Multiply this thing on the right. So this is y plus y x dash squared. We can then cluster the terms across in x dash squared. So this is going to be 2a x dash squared minus y x dash squared is equal to y. Then we can pull the x dash squared out. So x dash squared is 2a minus y equals y. Rebag up the constants. This is now x dash squared is equal to y on 2a minus y. And then we can take the square root of this thing. So we've got x dash is equal to square root of y on 2a minus y. Right. And then to go from x dash to x, we need to integrate both sides again. And so what we would have here is x is equal to, and let's leave it indefinite for the moment, integral of y on 2a minus y dy, okay? Right. An integral like this needs some special tricks, and the special trick that we use here is to do a substitution, right? So what we do is we substitute in y is equal to a 1 minus cos theta, okay? And so this is another one of these things that I'd keep in my mathematical books, book of tricks. Some of these square root integrals of square roots, you actually want to substitute in trigonometric terms because it cleans up the integral for you, okay? So let's have a look at how this works. What we've got now is x is going to be the integral of big square root here, a 1 minus cos theta on top. Let me just make that clear that it's a theta. And then on the bottom we're going to have 2a minus a 1 minus cos theta down the bottom dy. Now the problem is we've got this dy and we need to get it in terms of theta or we're never going to be able to solve this thing, right? This is the trick you use when you do substitutions. So what we've got is y equals a 1 minus cos theta. We had that above. dy on d theta is now going to be d on d theta of a minus a cos theta, which is just the first a drops out because it's a constant. The second term, the cos becomes a sine and gives me a minus sign, so this is a sine theta just here. And then we can rewrite this thing, oops, that's better. We can rewrite this thing as dy equals a sine theta d theta, okay? So then taking this integral out, the next step here is integral of, actually I want to move down just a tiny bit so I don't crash. Integral of, and let's set ourselves up before we use it. clean up this thing inside the square root. So this is going to be a minus a cos theta on a plus a cos theta. And then our dy is going to give us an a sine theta d theta over on the right-hand side, okay? And then we can cluster our terms in A in here, and we can let me think about this for a second. Where's this going? Actually, we can cluster them, and then they cancel each other out, actually. So these two cluster each other out, and then this A will go out to the front. This is what's going on. Okay, so this is now going to be A integral square root of 1 minus cos theta on 1 plus cos theta. And what I'm going to do is I'm going to bring the sine theta inside the square root. And when I bring it inside the square root, I have to make it a square. So now it's a sine squared theta d theta, okay, on the outside. All right. Now we know that sine squared theta is equal to 1 minus cos squared theta. That doesn't help us very much, but what it turns into does. So this becomes 1 plus cos theta, 1 minus cos theta, just here, okay? And so we end up with a integral square root here of 1 minus cos theta, 1 plus cos theta, 1 minus cos theta on 1 plus cos theta, okay? And so you can see here that this term kills that term. Then I've got the two terms here give me a square that kills the square root. And so what I'm left with is a integral of 1 minus cos theta. And it's actually really easy to... d theta. And I'm missing a d theta back up here as well, just for completeness. Okay. I can integrate this thing now. It's actually really easy to integrate. It's going to be basically a theta minus sine theta plus a constant. And so the last step in here, now that we've solved this, is just to attach some meaning to this, right? Did I have a step 3? Yeah, I did. Good. Okay. Just making sure I'm keeping in track. Okay, so what we have now is two equations for x and y in terms of a common parameter theta in here, okay? What we have is y is equal to a 1 minus cos theta, because we did that substitution to get this integral. And then we have x is equal to basically a theta minus a sine theta, or we could write this as a theta minus sine theta is actually the better way to write it. And we can ignore this constant off the end. It's basically just going to give us a displacement in our problem, and we can correct that by shifting the axes, okay? And so what we have here is essentially a link between x and y via theta that enables us to set what this path is going to look like. And we can sketch this path up now. Let's redraw our axes here. This is x, this is y. There's going to be a point down here called 2a. And if we think about what our y and our x do up here, you can plot this for yourself on a graphing program, but what it will do is it will go down to 2a and then come back up again and then go down to 2a, and it will just keep doing this, right? This is a thing called a cycloid. And basically, if you take a rolling wheel and you have a point on the outside of the wheel, as that wheel rolls, cycloid is the curve that you get from the point on the outside of the wheel while it's rolling along. Okay, it's a really special curve. And then this would be like a 0.3 in our problem. Our starting point up here is 1, and where we end our path is down here, so partway down this cycloid curve, okay? And so what we find is this cycloid is the fastest point. COVID-19 means I don't have a demo unit at the moment, and this demo is kind of hard to set up anyway. So what I'm going to do is take a calculated version for it. And so what we've got here is basically 3 tracks. We've got a roller coaster that comes down just on a straight line down to our point of interest where we want to get to. And this point of interest here might be you change the tracks afterwards and you go into sort of a loop or a corkscrew or something cool like that. We've got a track here that basically is the path of steepest scariness. So you just basically drop off the edge, go straight down, get down as far as you can before you're going to hit the ground and then pull out, okay? It's going to be some serious G down here, but that's okay. And then the green one in the middle is basically the problem we just solved, Brachistochrone problem, which gives us a cycloid curve in here, okay? And so what you can do is you can build 3 roller coasters side by side with the tracks just like that, kick them off at the same time, and let them run, okay? I wish I had bigger budget for the demo unit. I don't. And so let's run this thing. And you can see that the car on the green track has made it to the final point first. It's the path of least time. And it's some compromise between dropping your height and getting distance as you see the two, right? If you look at the video, you can see that the car on the green is winning all the way along because it's getting forward distance at the same time as it's getting its drop, and the other two fall behind because they're not taking the ideal path. Okay, it's probably a good time to leave it for today. So we've done a lot of work on minimizing paths. And so what we'll do in the next lecture is start to reintroduce things connected to paths like action and so forth, and build ourselves up to Lagrangian mechanics. I'll see you next time.